Hi students, welcome to lecture 23. Today we are going to discuss the induced drag and also look at some of the mathematical expressions which allow us to calculate induced drag, and we are also going to introduce the drag polar, which is very important concept as far as aircraft are concerned. I am Dr. Ranjan Ganguly. Now let's revisit the diagram which was very important from our previous lecture, and we take an airfoil section, and now remember we are considering a finite wing. So essentially we do have a chord line, we have the usual line here, and we have the velocity coming in this direction. And so what happens is that we have alpha. This is known as the geometric angle of attack. Now, we have seen that there is something known as a downwash which acts because of the vortices which are shed from the wing tips. And so what happens is that the actual flow direction changes because of this presence of downwash and the downward component of velocity. So the actual flow direction here is given by this green line, and therefore what happens is that there is something known as an effective angle which is seen by the wing section now, and this angle is in turn related to alpha and also alpha I. Alpha I is the angle induced because of the presence of downwash. So again, if you want to get more clarity on some of these concepts, visit my previous lecture and go through it. So there we showed that alpha effective is alpha minus alpha I. You can see it from this diagram here. Alpha effective is alpha minus alpha I, and we can clearly see then that the induced drag would be the component of the lift vector in this direction, which I have shown in red here. So this would be essentially L into sine alpha I, because this angle is also alpha I. And then alpha I is typically small because downwash is small relative to the usual velocity of the aircraft. So I can write di is approximately L alpha I. This is a very important equation. This is also telling you that the induced drag is coming directly from lift, and the second part of it is directly related to the induced velocity, because alpha I is of course related to the induced velocity. So now we are going to take recourse to some equations which have been derived before for us, and again, if you are more interested in these, you can refer to some books where they discuss the incompressible flow theory. So we will see in incompressible flow theory that if you have an elliptical lift distribution, that means the lift per unit span would vary elliptically along the span, then you would get uniform downwash, and in that kind of situation alpha I is CL by pi AR, where AR is the aspect ratio of the wing. So this is an important relationship which we are going to use today to derive an expression for induced drag. So in the previous lecture or slide, I pointed out that di is L alpha I, and therefore I can easily write CDI is di by q infinity s. That's the dynamic pressure into the wing area, and then I put in the values here and I get this relationship here. So again, all I am doing is I am taking lift and multiplying it by alpha I, and alpha I CL by pi r, and so I get this equation here. So this is an important equation which I have written in this yellow box, that CDI is CL square by pi AR. Now, how did I get this? You can clearly see here from this equation that di would be L alpha I, and L would be multiplied by alpha I, which is CL by pi AR, and so we get this value here, and therefore the drag coefficient comes out like this here. Now, when you look at equations, they tell you a lot of things, and this equation does tell you many things. So one of the things this equation tells you is that CDI is only present when there is lift. So it's directly related to lift. It's coming because lift is there. This is a very important concept, that induced drag is actually the price we pay for the creation of lift from a finite wing. Now, one more thing, we see that if the aspect ratio became infinite, then CDI would be 0. Therefore, for an infinite wing, induced drag would be 0, and that would be because of course there would be no downwash velocity here. So alpha I would be 0 also. Now you can also see that if I have a relatively high aspect ratio wing, something like this, if you are looking at a rectangle wing, then if I put this large number here, CDI would be less. So induced drag can be reduced by high aspect ratio wing, which would basically consider a long and slender wing type of situation, and in a low aspect ratio wing, induced drag would be more. So this is a fact which we see. The airlines which typically fly passengers, which have to cruise, which have to save money because they charge passengers for tickets, they tend to have high aspect ratio wing, and you will see low aspect ratio wing in situations where probably the government is paying for the flight vehicle, for example the military. So there these considerations of fuel may not be so important, at least in most countries. So let us now look at something which happens in the real world, and in the real world what happens is that E is defined as the span efficiency factor. So essentially this is introduced because we know that most real airfoils or real aircraft are not going to have an elliptical cross section. They are going to have something like a rectangle or a trapezoid or some complex cross section. So for example, if we did have an aircraft with an elliptical cross section, then E would be 1. So I modify CDI such that I write it as CDI equals CL square by pi E AR. And so E would be 1 for an elliptical platform like we discussed in the previous slide. But for all other platforms, let's say rectangle, trapezoid, or any kind of shape, E would be less than 1. And CDI is of course a minimum for an elliptical platform or planform, because in that case you see that E would be 1. Now for most subsonic aircraft, E would range from 0.85 to 0.95, and the closer you get to an elliptical planform, the better you are going to be in terms of E. Now, do remember that in the early days, like in the World War time frames, there were some aircraft which have wing platforms which are very close to elliptical wings. So it would be something like this. And if you go in Google and search for the pictures of the Spitfire wing, you are going to find that some of these are in this particular elliptical form, and therefore they would be pretty optimal as far as the equation we derived for CDI are concerned. In those cases, E would be 1. Now, totally the drag is composed of two components, the profile drag and the induced drag. So that's a very important formula which I have written here in this yellow box, that CD equals C small d plus CL square by pi EAR. Now you know this component, which is the CL term, this is induced drag, and CD is the profile drag component which we have discussed in some of our previous lectures, which has come from skin friction drag and also from pressure drag. So the total drag CD is given by these two components, and one of the graphs which is very important as far as aerospace is concerned is known as the drag polar, where we plot CD versus CL. So we have done that here, and you can clearly see that, for example, if CL would be 0, CD would be small cd, that's this location, that's only profile drag. And then as CL goes up, this graph will go up because all these remaining factors are all positive values. E is positive, aspect ratio is positive. So this would go up because we have CL square here, and even on this side if CL is negative, it would go up. So essentially this is a nice curve which you get in terms of CL and CD. Now the drag polar is something which is provided for many aircraft and wings, and it's a very valuable piece of information which you often get from a airplane designer. So if an airplane designer gives you this drag polar, then you have a lot of information about that particular aircraft or finite wing concerned. So let's now go back and look at some of the things we have discussed before. So again, we see here that flow on an infinite wing with angle alpha is same as flow on a finite wing with angle alpha effective. So we have seen before that if we have the airfoil section here and it had alpha, that is essentially one situation, and this is same as a finite wing section with angle alpha effective, and the relationship between alpha effective and alpha is given as follows. So it is essentially alpha minus alpha I, where alpha I is coming because of downwash. Now we will see clearly that the finite wing acts to reduce the lift curve slope. So essentially if we were to take this particular value dCl by d alpha minus alpha I, that would be A0. That means I am differentiating Cl with respect to alpha effective, and therefore if I integrate this equation I immediately get this equation that Cl is A0 alpha minus alpha I plus some constant. So we are going to try to now get a relationship between these two lift curve slopes, that is the lift curve slope for the finite wing and the infinite wing. So let's start with this equation here, and we also recall that alpha I can be given in this form if I consider alpha I to be in degrees, and then I can immediately substitute this in the CL equation and I get this equation here. So all I have done is I have substituted alpha I into this equation and expanded it out. Now I further expand this equation out, and then what I do is that I take the derivative A is dCl by d alpha, and I get it in this form here. So here you can see now that there are two lift curve slopes. A is the lift curve slope for the finite wing, and A0 is the lift curve slope obtained from airfoil data, which is actually the data you see in most of the books or in the appendices of many of the books. So this is the data obtained from wind tunnel test, for example. And so the relationship is given like this. So if for example you had A0 coming from airfoil data and you would require aspect ratio of the wing, you could require the E1 value, the span efficiency factor of the wing, and then you can essentially calculate whatever is the value of A for the finite wing. Now just by looking at this equation qualitatively, you know that this part is going to be some particular positive value, and therefore A is going to be less than A0, except for the case where AR would be infinite. Again we are seeing that also works out here. If AR is infinite, this term goes to 0, and in that case A becomes A0. So essentially one of the ways to make the lift curve slope as close as possible between an infinite wing and a finite wing is to keep increasing the aspect ratio of the wing, and in the limit as aspect ratio becomes larger and larger and finally becomes infinite, A would be equal to A0. So this is something very important. But now you clearly see that whenever we are getting data for an airfoil, it's very useful to us because I can use this airfoil data to get the lift curve slope for the actual wing. All I need to know is the aspect ratio and the span efficiency factor E or E1. Now there are some small differences between these values E and E1. It's linked to something to do with the profile power varying with lift and so on. But in most cases, we can assume these two numbers are going to be pretty much the same. So to summarize today's lecture, we got some quantitative equations now for some of the things we were talking about in the previous lecture. So we have a clear equation for the induced drag, that is CL square by pi AR, and we also saw that in the case of real wings which are not elliptical, we bring in this factor E here is the efficiency factor, and when E is 1 for an elliptical wing, you get back this expression here which is valid only for an elliptical wing. So the value of E is typically something like 0.85 to 0.95. Now we also saw that the total drag is the sum of the profile drag C small d and the induced drag, which is CL square by pi EAR. And from these three equations we clearly know that the induced drag could be decreased by increasing the aspect ratio. So that's one of the things we can do to reduce the induced drag. Of course, the induced drag is also always dependent on lift, so it's something which is like a price we pay for because we have a finite wing. Now, we also saw that the lift curve slope of a finite wing, which is A, is related to the lift curve slope of the airfoil or the infinite wing, which is A0 through this equation, which basically tells us that A will be less than A0. And again, we see that if the aspect ratio of the wing is increased, then these things can be brought closer together. So today's lecture, we got a lot of quantitative equations which we can use to calculate induced drag and which we can also use to get an estimate of the total drag of the finite wing. So we got introduced to the very important graph known as the drag polar, which is one of the fundamental graphs we use for any kind of aircraft design. So whenever you are talking of aircraft, very often people want to look at the drag polar as the first thing so that they can figure out something more about the aircraft concerned. So I'll end this lecture now and I will see you in a lecture sometime soon. See you then.